Log on, tune in, find out. Another good idea from Cambridge.
We proceed our pursuit of Hitchin modular spaces with another talk by a friend of mine for many, many years. It's a pleasure to introduce Emanuel Diaconescu from Rutgers, who is going to tell us about BPS states, Donaldson-Thomas invariants, and Hitchin modular spaces.
Thank you very much, and I'd like to thank the organizers for inviting me to speak here. So I was going to report on some work on, as Rutgers said, on BPS states, Donaldson-Thomas invariants, and Hitchin pairs. And this is work with Wei and Chuang and Gang Pan. So this work is trying to kind of connect several different topics that kind of up until now have been developed in parallel without much interaction to each other. So one of them is some work on the cohomology of Hitchin moduli spaces. And this is more specifically some work done by Hausel, Rodriguez, Villegas, and some recent results of Garcia Prada, Heinloth, and Schmidt. So that's one topic we're going to try to put on the blackboard today. Now the second is concerned with Donaldson-Thomas invariants of Calabi-Yau threefolds. So this is going to be basically the stable pair incarnation of this invariant. So the invariance is defined by Derived and Thomas. Although I'm not going to be very careful in distinguishing between DT and PT and in this talk. I mean, it's you'll see that in the end I'm going to just write down some formulas. But I think this is perhaps the best incarnation we have to keep in mind. And then the theory of Joyce Song and Kontsevich-Soibelman. Okay, and then the third is something that has been around for a while in physics and also in mathematics, the issue of BPS invariants or BPS states, which, as is well known, it follows the work of Gopal Kumar and Vafa. And also, so that's the physical papers that started it. And then there is some work in mathematics by Hosono, Saido, and Takahashi, which was actually very important in trying to make making all these connections. And finally, the other thing I'm going to talk about is geometric engineering, which I'm going to explain is going to give us some approach of kind of deriving formulas for motivic Donaldson, well, for refined Donaldson-Thomas invariants without actually understanding very well what the theory is. So this follows mostly work of Nekrasov, and also in mathematics, Nakajima and Yoshioka. So I'm going to just try to explain how all these things are connected, and I don't know if I have enough time, I'm going to mention also how it's connected with wall crossing. Maybe. Okay, so let's start with I'm going to start with a brief review of the work done by Hausel and Rodriguez-Villegas on Hitchin moduli spaces. Cohomology of Hitchin moduli spaces. Okay, so X is a smooth projective curve some genus G. Most interesting cases are greater or equal than 1. So we take, I'm going to denote by H, X, RE is just the moduli space of semi-stable Hitchin pairs. Now, Hitchin pairs means I'm in a vector bundle E on X and a Higgs field, which is a morphism from E to E tensor K of X. And there is a slow stability condition with respect to fine variant subbundles. That's kind of familiar to this audience, so I'm not going to insist on details. Okay, so, and then there is as mentioned by Tudor in previous talk, this is actually, I should mention that if R and E are coprime, that's important. These are coprime, this is actually a smooth quasi-projective variety. And more than that, it's actually hyperkähler. All right, so it's a hyperkähler manifold in that case. And in fact, if that condition is satisfied, you don't have strictly semi-stable objects. It's just stable. Okay, so then in a different complex structure, you can rotate the complex structure in this space, and you can look at it in a different way. So it's related by hyperkähler rotation to the so-called character variety. So let me call it C of X and G of R. It's just homomorphisms from phi1 of X minus a point into G of R, mapping the generator corresponding to the point to e to the 2 pi I over R times the identity. And it's modified by conjugation. So this is basically the variety studied by Hausel and Rodriguez-Viegas, the character variety. And there is, they obtain some deep results concerning the cohomology and Hodge theory of these spaces. So I should also mention something else, that this space H, the Hitchin moduli space of Hitchin pairs, comes with a Hitchin map, which is very important for us. So there is a Hitchin map which projects H down to an affine space, a linear space actually, base B, which is just a direct sum of spaces of sections of powers of K of X. And the important point, this has compact fibers, and it's generically they are smooth abelian varieties, and they degenerate in a complicated way over some discriminant. Okay, so now the question is how. So these spaces are diffeomorphic as smooth manifolds, but they are not isomorphic as complex manifolds or algebraic varieties. So the question is, how is the cohomology related? So there is a deep story here that goes, it's work of Hausel, as I said before, Hausel, Rodriguez, Viegas, but I'm going to denote this by HRV because I'm going to use these names a lot in this talk, so it's easier. So then also Hausel, Cataldo, Hausel, and Migliorini. So there is something that, well, I for the purpose of this talk, I like to call it something like it's perverse mixed correspondence. So what is this? Well, the issue is that since these spaces are the same as smooth manifolds, they of course they have the same cohomology. But if you look at Hodge structures, the Hodge structure and this cohomology, they are very different. So the major issues are the following. So if you look at the character variety, and let's put let's look at HK of this and HK of the Hitchin system. Well, what you know is, for example, here you have a non-trivial mixed Hodge structure. So there is a mixed Hodge structure, which is some filtration, some wave filtration. on the cohomology, and it has been proven that in fact there is a degeneration in this, in the sense that the successive quotients of this form are actually 0. So it's somewhat degenerate. So now you can ask yourself, well, this space, on the other hand, it also has been proven that this has a pure Hus structure. So you might might ask yourself, well, on this side we have a non-trivial Hus structure, non-trivial mixed Hus structure. What does this filtration correspond to on the other side? Is there a natural geometric description of this filtration on this side? So the answer was provided, as I said, in this paper by Cataldo, Hauser, and Migliorini, in which they argue that this filtration matches something called the perverse sheaf filtration. So it's denoted by something like P0 in P1 ... in Pk, which is Hk. So this is a very technical issue. To be honest, I don't know much about this. This follows from the Leray spectral sequence for the Hitchin map. So you use this. You take this map. As I said, it has some very degenerate fibers. So you employing the Leray spectral sequence, you can construct this perverse sheaf filtration using complexes of constructible sheaves. So and then their main claim is that these filtrations are the same. So that's one of the claims. It has been proven for rank 2, and it's a conjecture in general, if my understanding is correct.
What does this mean? That you give this modular space of lambda connections, and you vary this mixed core structure, and over 0 you have the x1, and then over generic point.
Okay. How you define this? I can't reproduce this definition. It's complicated. You just use you have to use the push forward of the constant shift here as the intersection as a perverse sheaf. So you get on the base, So you get a complicated perverse sheaf on the base, and then there is a way of using the Leray spectral sequence, which converges the cohomology of the total space, of actually filtering the cohomology of the total space. Okay, everything I know about this, I learned from Tomas. So
on the right side, that's H2K there, right? And these are the
I'm sorry, this was meant to be. Okay, I'm sorry, I apologize. Yes. All right, so the conjecture, so as I said, the result is that they are the same. The theorem is that they are the same for rank equals 2, and the conjecture is that it's true in general. All right, so that's the statement, that it's true in general. Okay, so now now to summarize the work of Hauser and Rodriguez-Villegas, so what they did, well, you construct for the character variety, you construct what they call a mixed Hodge polynomial. Polynomial of 2 variables. I'm going to use Q twiddle here because I'm saving Q for something else. So it's sum over the dimensions of the graded pieces in the weight filtration, e to the k, Q twiddle to the I over 2. And the properties of this is that it specializes in 2 ways. So for Q twiddle equals 1, it specializes to the Poincaré polynomial. And for t equals -1, if I got my correct conventions right, it specializes to the E polynomial. Okay, so now their main result is a computation of the E polynomial of these varieties using basically counting rational points over finite fields. So it's a formula that I like to write down because it's a very nice formula. So it's probably the only big formula I'm going to write down in this talk. So the result is very nicely summarized as follows. So you take, so this is the HRV formula. Okay, you take, so for any partition, so lambda is some Young diagram. There are many reasons to actually write this formula because you'll see later on why I'm writing this. So for each lambda Young diagram, I'm going to define a rational function of some variables, z and w, which is the product of all boxes, and z to the 2a plus 1 minus w 2l plus 1 to the 2g divided by z to l plus 2 minus w to the 2a, z to l minus w to 2a plus 2, where a and l are the arm and length of and leg length of a given box. So it's standard notation. So if you have a partition somehow, have a box in here, that's a and that's l. Okay, and so that you define this rational function, and then their formula says the following: if I make a generating functional by summing over all partitions of this rational function, it equals to some kind of plethystic exponential. So it's exponential sum over k greater or equal to 1 and sum over r greater or equal to 1, t to the k r over k, then something called h bar z to the k w to the k divided by z to the k minus 1 minus w to the 2k. Okay. So then so you define, if you want to, you define these h bars by this formula. So their statement is that this h bar essentially, so there is a, well, maybe I should go to the other side. So there is a conjectural statement, namely that the mixed Hodge polynomial we define there. So this quantity here for the character variety. Let me remind ourselves it's the character variety q and t equals something like this: t q twiddle to the 1/2. So the dimension of the character variety, h bar of q twiddle to the 1/2 minus 1 over t q twiddle to the 1/2. So there is some change of variables, but that's not the essential. The essential point is that this h bar conjecturally compute the mixed Hodge polynomials of character varieties.
R here is the rank of the.
R is the rank, yes.
Where does the R appear over
There should
there?
have been an HR here, right?
And where's the R?
Yes, I'm sorry. Yes,
Oh,
yeah, this is
one
h
T to the okay.
HR. Yes, you're right.
The degree doesn't play a role.
There is no degree yet because I'm just doing character varieties, but that's true indeed. In this context, I don't talk about degrees. Yes, you're right. I'm trying to move a bit faster. Okay. So the important point is this is conjectural. It's a theorem for this specialization, for the specialization to the e polynomial. So if you set t equals -1, it's a theorem. That's the main result. And then in general for arbitrary t is a conjecture. And the other thing to notice is that because of this change of variables, q in fact, so remark, q twiddle ends up being something like z squared when you make this change of variables. So in this formula here, you cannot take q to 1 to get some generating functional for Poincare polynomials because you have the denominator. So more precisely, the conjecture says that if you solve for this recursively, this ends up being a polynomial, and then you can do whatever specialization you want, but not before that. Okay, so that's basically in a nutshell the part of their work, that we will be mostly interested in today. And okay, so the next step I have to, and of course, if you believe this conjecture about the perverse mixed correspondence, then okay, good. So that's good because that's exactly the point about degree. So you can, what you learn using the perverse mixed correspondence, what you learn is that the same formula computes some graded Poincare polynomial of the Hitchin system, which is graded by this perverse degree, and another consequence of that is that it's completely independent of V. So so let me, okay. So the perverse mixed correspondence implies that, well, you have the same formula interpreted now as with respect to that grading, and it's independent of the degree E.
In the co-prime case or something.
In the co-prime case, yes. None of this works in the other case. Yeah, I should have said everything is coprime here. All right, so, okay. So I think that's, okay, good. So now there's another remark that I want to point out. It's going to be important later on. So another remark is the following. If we take omega to be a relative ample class for the Hitchin map, which was going from H to this affine base, what you get more structure. So first of all, you can prove that there is a relative Hard-Lefschetz theorem, and you can prove that the perverse filtration splits. So you can use the so you get a splitting of the cohomology of the perverse shift filtration in graded pieces. And I should call it something else. GRP sum over P. There is a shift. And moreover, what you can do, you can actually prove that there is, and actually this is also closely related, as I said, with the work of Hosono, Saito, and Takahashi. There is actually, if you do a little bit more work, there is an SL2 action. There is an SL2 action on this cohomology space, and multiplication by omega acts as a raising operator. And on top of that, you can actually enhance this to an SL2 cross C star action. So this only keeps track of the L is that's the difference between the homological degree and the perverse degree. So this is just the homological degree, and this is the perverse degree. Okay, so this is a bit less than you are used to in physics. In physics, physicists want an SL2 cross SL2 action, but in this case, because the base is affine, you don't quite get that. You get only this. You only get this structure. And then, of course, you can decompose the cohomology with respect to this action. So you break it into irreducible blocks. And so, of course, if you have this action, you can just decompose your cohomology spaces. And so as you can immediately, because you can guess, this is going to be important for connection with BPS states. So you can write the direct sum of some vector spaces, the sum over irreducible representations of SL2, and the sum over L, VRL cross R cross S to the L. S is the canonical irreducible of C star, the one-dimensional irreducible of C star. So you can break it like this. So this is going to be important later on when I'm trying to make a connection with the physical BPS states. Okay. Okay, good. So that's sort of as much as I want to say about this part of their work.
At the risk of slowing you down, do you happen to know what this decomposition is for R equals 2 and G equals 2? It sounds like a specific question.
Actually, no. It's a good no. I worked out many examples, but that was a few months ago. So and actually, I'm planning to write down some notes about this. I'm going to write the examples. Yes, it can be worked out in detail. These are compositions. I mean, it just yeah.
No, I have specific numbers that I would
specific
like
numbers. Yeah, I can produce specific numbers because I mean, using this formula, you can certainly. I mean, specific numbers for the dimensions of the spaces. That's what I mean. Yeah. Yeah. But I think I know why you're asking this. Yeah. So I think I'll probably somehow what I want to say next is probably going to, in some sense, answer the question. Well, we'll see. Okay, so let me just move to Donaldson-Thomas theory. I mean, here, of course, with this audience, I don't have to say much. I just want to mention a few things. So we are doing Donaldson-Thomas theory of what? Of a very specific class of threefolds. So we call Y is just a total space of O of x plus K of x over x to x. I mean, there is a slightly more general story in which you twist the story by an effective divisor on x. But in order to save some time and to keep things simpler, I'm going to just talk about this case. You can do this case too. D is effective. D is an effective device. All right. And of course there is a. If you notice, there is a C star action here. I'm going to talk about the anti-diagonal one with opposite weights. So in this context, the Gromov-Witten theory of this was studied by Brian and Pandaripande. And it was entirely computed with TQFT formalism. The Donaldson-Thomas theory was studied by Okunkov Pandaripande. Using so there are very explicit formulas known for these theories on these spaces, and in this case, in the case I'm interested in, I think I'm going to take the stable pair point of view. So you have so you can also think about stable pairs on this space, and of course you have some kind of virtual numbers of stable C equivariant virtual numbers of stable pairs, and they are certainly equal with the other ones. But what's important for us is that Kontsevich and Soiberman told us that there should be a motivic theory. So let me see. So let me call. Okay, maybe I should say a few things. So let me call PT of D and N is just the stable pair invariant of degree D over X and Euler character of the. I'm sorry, I'm really being sketchy here because this is so this is a stable pair invariant. So this is basically, in this case, it's an integer. It belongs to Z. So according to Kontsevich and Soiberman, there should be a motivic generalization of this. So there's going to be an invariant which is some kind of virtual motive of the moduli space of stable pairs in this geometry. So some motivic invariant. I don't have any insight into how to actually construct this invariant, so that's not the purpose of this talk. I mean, what I'm going to say, I'm going to work under the assumption that something like this exists. And tomorrow, I think you're going to see many more examples in which such invariants are very effectively constructed. And I should say that there is work of Brian, Berend, and Stensray constructing such invariants in certain cases, but not in this particular case. So you have this invariant, and then I want to hit it with a Hodge polynomial. And I'm going to get invariants that depend on two formal variables. So it's going to be some kind of polynomial invariant. And furthermore, you can specialize to a Poincaré type of invariant. So this is some Hodge type invariant and then a Poincaré invariant. It all relies on the existence of this. Once you have this, you can hit it with whatever. You can create more invariants. And the reason I'm doing this is because what I'm going to claim next is that there is a physics machinery that tells you how to compute these things without actually knowing what the theory is or how it's constructed. Okay, so that's, we actually leave this here. So there is some kind of a physics machinery that tells you how to compute these invariants without actually, as I said, knowing what the theory is. Okay, so that the machinery in question is known under the name of geometric engineering. Which gives you it's a machine that spits out formulas for these things. I mean, I'm going to describe what it is, but it's not. This is following the program of Nekrasov, and as I said before, there is work in math of Nakajima and Yoshioka. So in this particular case, what the idea is that you can get this invariant by looking at a 5-dimensional supersymmetric gauge theory and writing down some kind of equivariant K-theoretic flotation function, which looks like this. So you look at some rank 1 5-dimensional supersymmetric gauge theory. And I'm not going to try to explain what this is in physical terms, but the way to construct, so you have a k-theoretic partition function, which is constructed as follows. So for any k greater or equal than 1, take the Hilbert scheme of k points in C2. So there is here, I have a bundle. Vk is just pi lowest sag of this universal, the structure sheaf of the universal scheme, so the tautological bundle there. And I have another natural bundle, which is C sag of the Hilbert scheme. So out of these two bundles, I'm going to manufacture. Okay, I want to leave this there. So okay, so I'm going to manufacture the following K-theory class. So we manufactured the K-theory class that looks like this. Well, I mean, okay, so I can just say what the departation function of gauge theory is just 1 plus sum over k greater or equal to 1, q to the k, and then I have a chi-y genus, equivariant chi-y genus. I'm going to use y prime again here for reasons that are going to be clear in a second. Is the determinant of this bundle g to the k, 1 minus g, tensor C sag of the Hilbert scheme of C2, added g times. So I should put brackets here. And this t is just the natural torus action. So t is C star cross C star, and it acts on C2, and then it acts on everything. Okay, so you have this. So that's basically, that's what the physics input is. That you have to look at this thing, and then you can use a fixed point theorem to evaluate this. So it can be evaluated by a fixed point theorem. So you get some expression that lives in. It's something like this. It's a formal expansion in Q, and the coefficients are rational functions of y prime, and the equivariant parameters of t. So you get some expression that looks like this. Okay, so the expression, I should say, looks extremely similar to this. I mean, even at a superficial level, because it's a sum of partitions. I mean, for anybody who did this kind of localization computation, it's obvious. This is going to be a sum of partitions. And then you define, so then there is a slight change of variables. So then you say the refined Donaldson-Thomas stable pair theory of, so the refined dt/pt theory of this y is going to be something like the gauge theoretic partition function evaluated something like this. The details, of course, are not important. I'm just going to write this explicitly to show you that there is a very explicit formula you can write down. There is some formula, some change of variables, and then you produce some expression, and then physics tells you that it has to be this refinement of the curve counting theory of y.
So are you picking up the whole torus? So you use the anti-diagonal torus up here on
The
y.
anti-diagonal torus on y,
And
yes.
you're using the whole torus here. Those are different toruses? Or can you get say the diagonal torus instead of the anti-diagonal torus theory on the y?
I don't know how to do that.
You don't know how to get that.
No, I mean, see, this C2 is not, it's not the fiber of y. C2 in physics is this transverse space. If you imagine that you compactify empty.
This story doesn't say anything about the other directions on the diagonal torus.
No, but I have some thoughts about that, but maybe I can tell later, but not no. But no, the short answer is no. I don't know. I mean, there is a good reason for that, because that's the only action that preserves the holomorphic free form, so we get the supersymmetric theory. So, but I have some thoughts about, we might say something more. Okay, so let's see. Okay, so that's how you, so that's sort of the physics prediction for this. And okay, so now let's go back to this. So now we can try to see how is this related to this issue of BPS states. Okay, let me see, because I kind of messed up my. Okay, so.
In this prediction, if you specialize the Euler characteristic, then it's correct.
Yes, it's correct. It's correct. I know. I rechecked that. Yeah. Okay, fine. All right, so good. So now so how is this applied with BPS states? I think I kind of inverted something here, but BPS states. And then, well, okay, there is a slightly more complicated thing that gives you the UV, the Hodge type invariance. Okay, so BPS states, well, there's a very simple observation. So how is this related to BPS states? Well, it's a very simple observation saying that you can prove that if you take My, it's just the moduli space of stable pure dimension 1 sheets E on Y of degree D over with compact support. You have degree D over X, and then N equals chi of E. So I take this moduli space. So now basically from Gopal-Kumar and alpha, we know that somehow we should try to manufacture some BPS invariant using cohomology of this moduli space. Well, what happens is that if D and N are co-prime, you can very easily check that in fact this is isomorphic to a moduli space of Hitchin pairs on X. So that's how you establish a connection between the HRV formula and the work of Hauser and Rodriguez-Viegas and this Donaldson-Thomas theory. So there is a simple fact that MY dN is isomorphic to the Hitchin XD, and I think there is a shift here. But it's not together with shift anyway, because nothing depends on the degree if D and N are co-prime. Only for co-prime cases is that true. Okay, and then you can. So then you relate. Now you have but here this space has a lot of structure. I mean, we understand at least at a conjectural level. You understand many things about the cohomology of this moduli space, and well, you can. So then there is a refined Gopal-Kumar formula. This appeared, I think, first time it appeared in a work of Iqbal, Koskaz, and Vafa in the Torrey case, but it's certainly true in much more general terms, which says that this refined Donaldson-Thomas theory, so the refined Donaldson-Thomas theory, the refined of Y, now it has to be written as an exponential of something else, FGV of Y. So now I'm going to just write down a conjectural formula for this FGV in terms of the cohomology of the Hitchin system. So following the general, as I said, following the original GV formula prescription and also the refinement pointed out there, you can write down what FGV is supposed to be.
In this isomorphism, can you write like where a stable pair, how a stable pair goes to?
But the sheaf is not there.
This is just I'm doing this is pure dimension 1 sheet, stable, slope stable, pure dimension 1 sheets. There's no framing. I'm not framing them.
Okay.
I'm going to maybe say something. Yeah, I probably have time to mention so what happened to the pairs, but yeah, this is just for sheets. So that, in other words, this is some refinement in terms of, and to relate it to the works in mathematics, this is a refinement of the strong rationality conjecture of Pandore-Pandey and Thomas. Okay, so what is this FGV of Y supposed to be? Well, it's something like this: sum over k equals greater or equal to 1, sum over degree or the rank t to the kr over r over k. Then I have a sum over, now that's why I insisted on, let me see if I still have it. Yeah, I do. So, okay, look at it, that decomposition, then I have a sum. So let me call n the dimensions of these blocks. Those are called n, they're independent of degree. Let me see, so minus 1 to the L, 1 minus q to the minus k, 1 minus q to the y inverse, q y inverse to the minus k, trace in the representation are minus q to the k to the j, and J is the Cartan. So J in SL2 is Cartan. So that's just a character of this thing. So basically, that's the only slight, difference with respect to the physics literature is that here we don't have the SL2 cross SL2 action. There is only a C star action, this degree by L, but it's sufficient to write down, at least at conjectural level, a formula like this. So now we can put everything together. So what we have is we have this identity here. Well, conjectural identity. This is some refined Donaldson-Thomas theory. It was computed, well, if you want, predicted by physics in some way. Then it's also predicted by physics that it has to have this form. And the striking thing is that if you go and if you perform the right change of variables, you recover precisely the HRV formula. So that's actually something quite surprising. So this is actually by some change of variables. It's the HRV formula. It actually took us a while to really understand this, because it's not so obvious when, well, it depends how you write them, how you write these partition functions. But a priori, we kind of computed this in a different way, computed this independently. We worked with it, and then after a while, we realized that actually this is the same. And this is actually, we had many discussions with Tomáš Hauser and Fernando Rodriguez-Viegas, and also Sergei Mozgovoi, who helped shaping up this picture. So the bottom line is that this formula that came somehow from a different universe, in which came from counting rational points on character varieties, it's somehow reproduced by all this kind of Donaldson-Thomas / string theory arguments.
What is the change of variance?
I can't write it down explicitly, but it's simple. It's monomial. It's a monomial change. It just writes this.
Oh, it's a very simple thing.
Yeah, it's not a complicated thing, but it's a monomial change of variable. As I said, I'm going to write this, with some explicit notes, but yes, it's a monomial change of variables. It's just a matter of realizing that you're looking at the same thing in the right variable, in the right. Okay, so that's one. So that's basically one of the messages I wanted to what I wanted to say today is that this is a different kind of interpretation of this formula coming using physics terms. And then I can, since obviously I have enough time, I can say a few words. Let's see if I want to add something here. Yeah, I can say a few words on what does this have to do with wall crossing. So one of the problems here is that, well, you might think, well, what's one way of trying to prove this, or part of this, or something like that? And it turns out that.
Since you do have some time, can you say what this has got to do with BPS states?
What happened?
He's asking what it has to do with BPS states.
Yeah, the BPS states are elements in this vector space, in this cohomology space. That's what. It's really the physical. This is what the physics. This is very close to the original physical motivation for thinking about BPS states.
All of it, or some of it, or the V's, or what?
No, this is just the decomposition in irreducible representations. All of it, sure.
All of it. All
Yeah,
of it.
but this is going to tell you how they transform under the SL2 action.
BPS space is the whole of that H dot of A.
Yeah, that's right. Yes, and it's all summed over in this expression. Okay, so yeah, so let me spend maybe 5 to 10 minutes talking about how is this related to wall crossing. So there is some connection to wall crossing, but the problem is wall crossing. So it's familiar to the experts in the area. What happens is that in order to you have to work with Okay, so what you can relate to out of this formula, you have to take a specialization that's kind of not really allowed. You have to specialize to z equals 1, and then if you make that specialization, then you get then these polynomials here, they specialize to Poincare polynomials, or more generally Hodge polynomials if you work with a bi-graded case. So what's the connection to wall crossing? Well, The connection is the following. So if you try to if you imagine it, you try to now you go back to, I think it's related to Jim's question. So if you look at the moduli space of stable pairs,
I thought everything was already known in that specialization.
which specialization?
When you specialize the hodgepodge into the
Known in what sense?
I mean, you have a formula here, they have a formula there, you can inspect them and see that they're equal.
Ah, you can do that, but I'm saying there is a kind of a context that gives you a way you might try to relate them in a more geometric way, and perhaps even prove it if this program of motive-equal crossing is completed in this case. I mean, this formula is just a formula, but if you ask yourself how would you even, understand it in a more geometric way, it's not easy. I mean,
but you're not trying to access the perverse filtration on the Higgs moduli space.
no, I'm not going to access that. I'm going to just access the Poincare Hodge polynomial of the Higgs moduli space. That's the problem with wall crossing. It kind of doesn't see the information contained in there. But that's the only thing you can see. So the issue is that you can imagine. So if you think about, I mean, it's this idea of, again, it's the idea that in the third paper of Derived and Thomas, that if you take a stable pair on Y and you forget the fading data, then you get a sheaf, but the sheaf in general is not stable or semi-stable. So not a stable sheaf. So then the question is how you relate the two moduli spaces, and the framework for doing this is wall crossing. It's very similar to what appears in Toda's papers. So except in this local case, there is a way of doing this by using entire data on X. So you can, for wall crossing, you can set up your problem in such a way that you can only think about some kind of quiver sheaves, a category, an abelian category of quiver sheaves on X. And it looks something like this. You have quivers with two loops and two others going like that. And this is O. This is some bundle E on X. So you can, and there is a quadratic relation. So you can use this abelian category. So there is a natural notion of delta stability, so some parameter stability. That is, it's very natural in this literature on quiver sheaves. And then what you get is a chamber structure. So you get a chamber structure. So if you fix D and N, the numerical invariants, you get a chamber structure. This is 0. So if you move far away to the right, the theory stabilizes to the stable pair theory. So it just it is D and N. If you move far away to the left, it stabilizes to still to stable pair theory, but up to a reflection. And then what happens is, if you try to study how these invariants change when you change the stability parameter, you have to employ this wall crossing framework. Either Joyce and Song or Kontsevich and Soberman. Actually, it has to really be refined, at least refined, if not fully motivic. And what you find is that there's going to be. So this is connected to this question about. So now there exists some. You have some. Let me call it H of. Too many things are H, but. Okay. H of D and N is some generalized of Y. It's some refined, generalized Donaldson-Thomas invariant, which is sort of, it's a conjectural refinement of the invariance defined by Joyce and Song. And this is something in general lives in Q of Y. And it's for if D and N are not primitive, then this lives in Q of Y. And then you can write a conjectural wall crossing formula for this invariant. And what you find is you get a recursion relation. So you get something like, if you compute this difference here, some technical issues. I mean, you just have to sum up all these walls, but okay, that's fine. You get some relation that looks like this. So you get D and N, and you get some kind of universal factors. So it looks like y to the n minus y to the minus n over y to the n minus 1. And then you get lots of corrections. You have a big series of corrections I'm not going to try to write down now. You can write them down very explicitly, but what's important here is that all these corrections, they depend on invariants of the form pt of d prime and n prime and hd prime and n prime with d prime strictly smaller than d. So there is a very explicit formula, but I'm not going to try to write it down. So the important thing is that this actually, if you assume that you know this theory here, which we did, gives you an effective recursion relation for the h's. And these h's are now here, d and n are allowed to be non-coprime as well, at the price of having this invariant being actually rational functions of y. And and this is as I said, it's a recursive formula. It determines all the h's, and presumably it's related to this recent work of Garcia Prada, Heinloth, and Schmidt, which basically it's based on an application of this Hagden-Narasimha recursion principle to Higgs bundles. So somehow this coming out of string theory is somehow also in some sense some kind of looks like a Hagden-Narasimha recursion relation for Higgs bundles, but it's not clear exactly how they are related, or if it can be made rigorous. But you know, if all this program can be made rigorous, then this is going to give you a proof of part of the conjecture, part of the Hausel conjecture. And I should say actually here, I should mention that there is very nice work of Sergei Mozgovoi, who proved that the solution to this recursion relation actually satisfies this formula. So that has been proven rigorously by Mozgovoi. And I think I can stop here.
Question?
I was a bit confused about which part of Housel's conjecture which part of Housel's conjecture does this prove if it works?
The one in which you take q to 1.
Which one is that?
You get the Poincare polynomial in this case.
The Poincare polynomial or the virtual Poincare polynomial?
These are smooth spaces. You get the Poincare polynomial.
They're not the same. I mean, that doesn't mean they're the same.
Just get the Poincare polynomial. There is no support
Like
condition.
the one that comes straight from homology.
Yeah, from cohomology. From cohomology. With no support condition. I mean, no compact support.
The thing you were doing at the end, didn't Toda do this, just not in the refined case? Or?
Yeah, it's very similar to that.
You just need Toda to refine what he did.
Yeah, I mean, it's basically I mean, you can say anyway. I mean, if you complete the Conservier-Soberman program, then.
So earlier you mentioned that you could also, this is all for the k plus o local
Yeah.
theory, right? So
Yeah.
the other sort of kind of natural one is square root of k plus square root of k. What do the formulas look like in those cases?
But okay, the only thing I can do then is write some guess from physics for what it has to be. That doesn't.
And so we know what, so the limit, the Euler characteristic limit is setting which variable to 1 here? The one where you're just getting the numerical dt invariance. That's
then okay, you want.
Q is minus 1, right? So I mean, so we know what those formulas all look pretty nice. It looks the nicest in the square root of k square root of k. That's just why I was asking.
Sure, but that formula will come out of physics, but
Won't be related to the Hitchin system.
well, no, because you see the problem if you don't have. Okay, in that case, the Hitchin system gets replaced by something else, which is it gets replaced by. I mean, what I'm saying is this moduli space of pure dimension 1 shift. In that case, it's actually singular. And it's replaced by it's Higgs bundled with rank 2 coefficient. So it doesn't be replaced by data like this.
Square root of k.
Yeah,
I see.
and then phi 2.
Ah, I see. So you've made it so it only moves in one direction.
Exactly. Yes. So then you want a commutation relation here,
I see.
and I can prove that this is a smooth space. So if you had a, I don't know, well-defined cohomology theory for this space, then probably, but I haven't. No, there is no. Yes, without condition moves only one direction.
Questions? not, let's thank Emanuel again.